board. So here for the last lecture of this very nice course, thank you, Jaqueline, for this opportunity for all of us. So please, Jaqueline, we're waiting for the last lecture.
Okay, thank you. So thank you all to be back here. That's our last class. I hope we have enjoyed so far.
Jaqueline? Jaqueline? Some technical problem. Jaqueline? Hello? We lost Jaqueline. I think we lost Jaqueline. Okay,
yeah, maybe.
Guilherme, I'm going to put you also co-host because you remember one time also my internet collapsed. So it's good that someone is co-host. So Zoom persists if some of the co-host is still there. So let's wait for Jaqueline.
I'm sorry.
Here it is.
I don't know what happened. My internet dropped. Am I here? Can you hear me?
Yes, we can hear you.
Okay. It's saying that my internet is unstable, but can you hear me fine now? Yes.
Yeah. Okay.
So let's go back. We were talking about the Boltzmann that established, he believed, his hypothesis was that for almost every initial state, the time average of any observable would converge to the space average of this observable. So if you take the average in time or the average in space, it would be the same. So I already told you, spoiling in the first lecture, that this is not true. The hypothesis was showing to not be true in general, but it leads to the whole ergodic theory, because thinking of, okay, this is not true in general, but which conditions should we impose to the system for this to be true? And this is exactly ergodicity. We will see that if a system is ergodic, then this always works. But let's understand a bit better this hypothesis. So let's try to see with let's try to rewrite this with more like a physical point of view. What we have so far, we have studied the following. We have a dynamical system. We have a dynamical system, which is a map acting on some space M. Our map space, you have a point X, and then you apply the map to this, and then you obtain another point in this space, because your map is acting here. You obtain another point. This point is the time evolution of this X. So you have X, and then you apply, you have Fx, and then you apply again, you have F composed to Fx, which we call it F2x, and so on, Fnx. All right, so that's what we understand. So let's keep this, and now let's look at in another point of view. So our space is the phase space of a physical system. You can think that it's a box with some particle of gas inside. So the points in the space are the particles. And then you introduce another element, which is an observable. In physics, that's very important, because the observable, it's what you can measure it empirically. Let's think that if you have a box, the box is your space, the particles inside are the points in the box, in the space, in the phase space, and you move these, the particles are moving, and then let me do a drawing. The particles, you have your box, you have some particles there that are the points, and let's say that, well, you had one particle here, and then after a unit of time, it went here, fx. But you could think to measure the speed for which this point, this particle went to this other. There is a okay, it stopped the interference. So this particle went to this other particle, okay, but you could try to measure the speed that it went. So this is your observable. It's some measurement that we'll do, but the observable is not a map, it's not a dynamical system. The observable is simply a function. So it considers a point inside of your space and attributes to it, associates to it a number. Now, what you are thinking is the following: your space have the points, but each point has can be given a different weight. Think about that you have a bag of coins and you throw it on the table. So you have the coins are your point on your space, but each coin has a value. One is $1, 50 cents, a quarter of a dollar. So each coin has a different weight for this. And let's say that your observable would give you the value of each coin. So the coins are the points, but the value of the coin is given by the observable. So the importance here is that the image is on R. So you are giving a value for it. So in general, you want to study the auth of the points. So you have X, have Fx, and Fnx. But now each point have a weight different given by this observable that you fix. And instead of looking for X, Fx, Fn of X, you look for phi of X, this is gonna be a number. Phi of Fx, this is gonna be another number, and phi of Fnx. So, but these now are numbers. So you could add them and then divide by n, take the average. So let me see, I think I wrote. So in general, to measure a physical quantity, you can do this. You can do repeatedly measurement in time. What does it mean? You consider X and then you take the measurement of X. What the measurement of X? It's phi of X. And then you consider Fx. And then you take the measurement of Fx. The measurement of Fx is only phi of Fx. This is a number. This is a number. This is a number. This is not a point in the space anymore. It are numbers, real numbers. Then you can simply add them. So you look at your orbit to the time n, 0 to n. And then n minus 1 to have any numbers, n minus 1. And then you add all of them because they are numbers, and then you can divide by n. This is the average. Well, so this is exactly what is written here. You evaluate your orbit through the function phi in the observable phi, and then you add all of them, and then you divide it by n. This is the time average that Boltzmann's meant. What he expected was that in the limit, when you take the limit, when n goes to infinity of the time average, this should be the space average. But the space average is exactly the integral. So what his hypothesis says is precisely this. You have a phi that is integrable, any observable, it's a function, we call it, it's m to r. You have a measure that is invariant. In physics, existence of an invariant measure is equivalent to the system to be in equilibrium. So for an equilibrium system, you have an invariant measure. So you have your system in equilibrium, so you have an invariant measure. So the time average asymptotically converges to the space of average. But this is not true. If we just consider invariant measure, this is not true. For an invariant measure, you cannot say this. But this is true if we consider ergodic measures. For ergodic measures, this limit, it's precisely the integral, and that's what the statement of Birkhoff's theorem that we will see soon. Okay, so before we see this more general statement, let's focus and try to understand the dynamic point of view of it, because our idea is the following: we want to understand orbits. We want to understand what happened with give me a point. So look at the orbit of it, x, fx, f2x, and so on, fnx. What happened with this set? Where it accumulates or not, where it's visiting, which sets are visiting. So that's what we want to understand. And with this former statement, it's hard to think of the orbits. But let's see what can you understand if we restrict a bit our interpretation. Okay, so fix a point x and consider a set that is measurable. So you have your space. Again, you are back to the map, measurable map, and an invariant measure. Okay, so choose a set inside of this, any set that you can measure, E. What do you want to do? You want to check how many times fix a natural n. From 0 to n minus 1, you have any times. So how many, what's the fraction of this time, 0 to n minus 1? How many times this point x enter in the set E? So how do you compute it? You have a point x here. It may be outside of E, but then enters in E, and then goes out, and then stays out, and then enters again, and then you go up to n minus 1. Okay, enters again. So for this x that I chose, it enters 3 times. If I did n equals to 10, it enters 3 times in this set. So how do you compute this in general? You do the following. Well, you look at the cardinality of the set for between 0 and n minus 1, such that the fj of x belongs to E. So what you are doing, okay, between 0 and n minus 1, you enters in E a few times. Let's say k, but then you divide by n, because this is going to be the fraction of the time n that you enter inside of E. So for each point, you can write this number. Fine. Well, we want to rewrite this using functions. So we will introduce an observable to rewrite this number using a function. So think of the characteristic function. The characteristic function simply gives image 1 or 0. You fix a set, the characteristic function on this set is 1. If the point that you are applying the function belongs to the set, and it's 0 if it doesn't belong. Okay, for points inside of E, the image of the characteristic is 1. If for points outside of E, the image of the characteristic is 0. So you can rewrite this number. This number is precisely the fraction of time between 0 and n that the point x visit the set E. Okay, so can you write the following way? Well, instead of writing as a cardinality of a set, you can write as a sum of functions. You can write this as an average of observables. Recall that an average of observables was 1 over n sum phi fj x j between 0 and n minus 1. So you write exactly like this, but with the phi being the characteristic function. Well, let's check. The characteristic function of fjx gives 1 if fjx belongs to E, is or 0 if it doesn't belong. So in the sum, you add 1 if the point is there in the E, and you don't add anything if the point is not. So if you varies J, you have all the sum. So you have exactly the cardinality of this set. It's fine. So finally, we can define the frequency of visits of X to E. So you have your set, any set measurable, you have your space M. You choose any set of that is measurable. I'm not saying that they are positive measure. I just say that I can measure it. So choose a set that you can measure, and then you can. Sorry, I'm adjust here to see you because I cannot speak without seeing anyone, and now it's better. Okay, so so you have the set inside. Then you want to compute the frequency of visits. What's the frequency of visits? Let's think about this. It's you have a point, and then he enters inside. So recall a bit the Ponca recurrence theorem that we saw in the second lecture, or first, maybe first. Yeah, first lecture. We had what Ponca says: if the measure of a set is positive for an invariant measure, so almost every point enters in this set infinitely many times. It says that it enters infinitely many times, but it could be that it enters once and then it spends a lot of time outside, a lot of time, but a lot, and then enters again, and then it spends a lot of time again inside, and then enters again. What do you want to know with this number, the frequency of visits? It's how frequent a point visits a set. How is the frequency that they visit? Because it could be that this frequency is very small. It's still you visit infinitely many times, but it's too small. Imagine that your mother lives 100 of years, and if you visit her every 6 months in 100 of years, it's a lot of visits. But still, every 6 months, your mother is going to be very upset. She'll think that the frequency is not good enough. So to understand the frequency, it's important. So let's study a bit this frequency. So the difference of understand this frequency for the Poincare theorem is this. We have a much more precise way for defining the visits. So again, we are trying to understand the ops. We cannot say precisely for each opt what it's going to do, but we are having some information. Through the measure, we will have some information. Okay, so in the end, our frequency is simply the limit of these averages. So the limit of these averages of observables for any specific observable, which is the characteristic. Well, this limit may not exist. There are cases where this limit does not exist. But when does it does exist, we know the following, that the frequency of visits of a point to a set is equal to the frequency of each point in the opt. Well, we just proved that it's equal to the visit to the image of it. So if a point and its image has the same frequency to the set. Well, by Poincare, we know that it's going to be infinitely many times. But, and the point is in the opt, it's still, let's prove it. Okay, so we have to prove that the frequency of visits of fx to e is equal to the frequency of visits of x to e. So the frequency of visit of fx, it's actually the limit when n goes to infinity. The definition is here. You take 1 over n, characteristic j 0 to n minus 1. But then you have fj, and instead of x, you put fx. Well, this is going to give you fj plus 1. You can here write this. It's just here write. And instead of put j plus 1, you can start j by 1 and goes up to n. And here write this fx. Okay? So that's the frequency to fx. All right. But this is actually, you can write like this: the limit of n going to infinity, 1 over n, the sum j. Let's write 0 to n minus 1. The characteristic fj x, fine. But this starts in 1. So I add 0 here. So I subtract 0. I put 1 over n, characteristic. When j is 0, you have f0 with x. Gives you x. Fine. You also stop in n minus 1, and before you had n. So you have to add the n when j is equal to n. So to add, I'll write like this: minus, and 1 over n is already there. I put characteristic of e when j is equal to n, you would have fn x. Okay. Well, my handwritten is horrible, but what is in this part is the frequency of visits of x to e. So what we have to prove is that this goes to 0. The limit of this part is 0. Well, this goes to 0 because you have 1 over n times, so 1 over n goes to 0. But you can think that this is bounded. This is bounded because the characteristic function is 0, 1 always. And then you are subtracting, then this is going to be 0 or 1. It's always bounded. So you have a bounded times a sequence that goes to 0. This goes to 0. So this is precisely the frequency of visits of x to e. So it doesn't matter in the opt, it doesn't matter the point that you choose in the opt, they all have the same frequency. Okay. Okay, so a more less general version of Birkhoff's ergodic theorem with this, thinking of the frequency of visits, we can write the following. Well, if you have an invariant probability measure, so you have an invariant probability measure, for almost every point you fix a set, for almost every point, the frequency of visit to this set exists, because it's a limit that we said, well, it may not exist, in general exists. And moreover, you can say that the integral of these frequencies are precisely the measure of the set. This is not good enough. What we want is that, well, for almost every point, all the frequencies of these points are equal and are precisely equal to the measure. Here you have to integrate. You have to integrate along the set, along the space, with respect to the measure mu. So for each x, you may have different frequency of visits. We would like to say that the frequency of visits of a point to a set is the same number, is the same as the importance that the measure gives to the set. Because the measure of a set is like, okay, a measure look at the space and see the sets and gives, oh, this measure 1, this measure 0, this measure half, this measure 1/4, this measure log over 2. So the measure is the decide the importance of each set. Think again about the coins. Now, this coin is $1, this coin is a quarter, this coin is 50 cents. Fine. I don't know if there is 50 cents, probably, but there is in euro 50 cents and in reals also. But anyway, so you have the value of the coins. So that's what the measure is giving. It's giving some weight. So you wish to make it sense, the frequency of visits to this set should be the same as the importance that the measure gives to it. If the set is too small, if the measure of a set is 0, the frequency to visit this set should be 0. because the idea is that you don't study the points that are in zero measure sets. You ignore them. But if the points visit this set, so shouldn't ignore. So this is not good. So for makes more sense for the measure to be better to understand your system, the frequency of it should really be the same as the importance of the set. So we saw that for invariant measures is not true. We have to integrate, it's not precisely this. You already have some answer, but it's not this. But we'll see that for ergodic measures, it is. It is exactly what we want. Okay, so again, the frequency of visits we wrote as the limit of this average for a characteristic function fj. But again, the average can be generalized changing this characteristic by any integrable function. So now the Birkhoff's general versions of the Birkhoff's ergodic theorem is this. If you have an invariant measure, so the hypothesis is that you have an invariant measure. If you have an invariant probability measure and you take any observable, but it's enough to be integrable. So you take any observable which is integrable, then when you take the average, for almost every point it exists. And moreover, if you integrate the average, then it is exactly the integral of the observable. So it's exactly this is the space average. We call the phi tilde, this is the time average. You'd like that the time average of this observable was equal to the space average. It's not. It is its integral, the integral of the time average, it's equal to the space average. You would like to throw away this integral. Well, for invariant measures, you cannot. But before we show this result for the same result for well, let me make a stop here. This is a very strong result. I'm showing it in a way, well, it's not precisely what we want, but this gives a lot of information and has many applications. We'll see a few. And it's a nice theorem, and the proofs, there are different proofs, but the proof is, at least the ones that I know are very nice. And unfortunately, I don't have time to do it. It's a long proof, all of them. But they are very nice. And this is a very strong result. This is really very nice. There are other ergodic theorems. There is also the Kingman's theorem, subadditive theorems. There are other ergodic theorems, but this is, let's say that this is the most base. This is at least for me, is the nicest. Okay. So before we state the result for ergodicity, the Birkhoff's theorem, when in the case that the measure is ergodic, let's try to write different equivalent definitions of ergodicity. Because I think Assad asked me last lecture about this, and well, this is important to talk, especially we have to make the connection between the Boltzmann hypothesis with the ergodicity that we have. So let's recall that an invariant set is the set that the preimage is equal to the set. So take the preimage, this is equal to the set. When the map is invertible, recall that it is equivalent to be image of a set equals to the set. Then a probability is ergodic if for all invariant sets, there is only, you cannot, I wrote this wrong. Sorry. This is not this. I don't know why I wrote it. It's ergodic if the measure of all invariant sets either is 0 or 1. It's precisely the opposite. Okay, it's precisely the opposite if there is no invariant sets for which that happens. So it's either 0 or 1. you cannot decompose your system. But now we need to relate to that Boltzmann hypothesis that it's about average time and average space average. So let's introduce the concept of an invariant function. So a function is said to be invariant if when you compose with the map, so the map it's defined on M. So you apply the map, it goes to M, and then you can compose with psi. So if you compose with the map, it's equal to the function. It doesn't change. It means that along orbits of the points, the function gives the same value. Remember, we are saying, take phi and look at the orbit and average. To do the average, you look at the orbit of a point x, fx, fn minus 1x, and then you take the measurement using your observable, which is your function. You apply phi, and then you add it. And then you divide it by n. That's the average in time. This is a number. Okay, if your function is invariant, when you apply psi, all of these are going to be equal. So what you would have, it's going to be n psi x, let's say the first one that you apply, and then it's precisely psi s. So if you have an invariant function, the average in time is actually the function applied on a point. Okay. I don't think I need to, yeah. So what we can state is the following. It's equivalent for a measure to be ergodic if all the measurable sets, the frequency of visit of a point to the set is precisely the measure of the set for almost every point. So you fix a set, choose a set, consider the frequency of a point to the set. This is precisely the measure of a set for almost every point in the space, in the whole space. Okay, so it means that there is a set. When I say almost every point, I think I mentioned this many times, but maybe it's good to comment this, that it means that there exists another set containing M with measure 1, for which these hold, the proposition hold for all the points in this set of measure 1. That's what means that something holds almost every point. There is another set inside that has full measure 1, the maximum is 1. We are considering probabilities. Then it holds for all the points inside of this set. Fine. And the last equivalence is that with functions now. So first you have an equivalence with the frequency of points, and now you have an equivalence with invariant functions. So if a measure is ergodic, it's equivalent. No, a measure is ergodic if and only if every invariant function is actually constant. Well, constant almost everywhere. It means that it's constant for a set that has full measure. Well, I'm not sure how much is my time because I forgot to put the timer.
Yeah, you have a lot of time. Yeah.
Great. Yeah, great. Okay. So let me. No, I still have many things, but at this point, I would decide if I do the proof of this proposition or not. And I should have put my time, but I forgot. Okay. So I'll try to give some ideas at least of the proof of this proposition.
You still have half an hour, so it's okay.
I think I dropped. Okay. You can still hear me well. Do you hear me well? Okay. Okay, thank you. So the proposition is the following. It's the equivalent definitions for ergodicity. So we have that the measure is ergodic if and only if the frequency of a visit to a point to the set, to any set, is the measure of the set for almost every point. And I'm just rewriting informally here so we remember what we have to prove. And for every function which is invariant, then this function is constant almost everywhere. Okay. So what we'll do is the following. I don't know why I wrote like this, but I will prove 2 implies 1. Then I will prove 1 implies 3. Then I'll prove it needs to be closed now. Then I'll prove 3 implies 2. Okay. So then it's fine. Now 2 implies 1, 1 implies 3, 3 implies 2, then it's fine. So let's start by 2 implies 1. So we need to prove that if these hold, if the time average, if the frequency of points that visit is equal to the measure of the set for almost every point, then the measure is ergodic. Well, to prove that the measure is ergodic, you have to prove that for every invariant set, either the measure is 0 or 1. So let's take A, an invariant set. I need to prove that the measure of this set is 0 or 1. Well, if it's invariant, it means that the pre-image of this set is exactly the set. But it means that it implies that if a point is in a set, well, it is in this set if and only if the image is also in this set. So a point is in a set if and only if the image is also in the set. So if a point in this is in an invariant set, all the opt is in the invariant set, and it holds the opposite also. If a point, any point in the opt is in the set, so the whole opt is in the set. For an invariant set, this is invariant by the beginning. Okay, so it means that the frequency of a point, take a point on M, it may not be in A. If the point is in A, what's the frequency of visits to A? Well, if the point started in A, the image is going to be in A, the other image is going to be A, so it is going to be in A forever. So if the point's in A, the frequency of visit to A, it's 1. Is the whole, because remember, the frequency you divide by N. So it's the fraction of time, so you are dividing by N. So at fixing N, it means that up to N you visit every single time, and then you divide by N, it's 1. The whole time you visit this set. Well, here it's because the set is invariant. That's the hypothesis. Fine. And if the point is not in A, so then the frequency of visit is 0. Because if the point is not in A, so none of the points, if it's not in A, none of the points is going to be in A, none of the points in the opt. So the whole opt is going to be outside of A. So it's never going to visit A. So the frequency has to be 0. It's never going to enter in A. So there is only 2 possibilities, or the frequency is 1 or the frequency is 0. But the frequency for each point, we are supposing that the 2 holds. We want to suppose 2 and prove 1. So by 2, the frequency is precisely the measure. So the frequency can be just 1 or 0, so the measure can be just 1 or 0. Okay, it means that I choose a set that is invariant and I prove that the measure is equal to 0 or 1, then the measure is ergodic. Okay? Well, now we need to prove that if it's ergodic, then every invariant function is actually constant. Every invariant function is actually constant. So let's prove this. So it's E1 implies 3. So if me is ergodic, then for each invariant function, it's constant almost everywhere. All right, so let's consider psi an invariant function. Well, recall psi it's a function that satisfy psi composed to F, it's equal to psi. And psi goes to R, it's a function. So choose an interval, any interval. So if you consider the set A to be the pre-image of this interval by psi, so A is invariant as a set. So there are the same words appearing 3 times. There is invariant of three different things. The invariance of the measure, which means that the measure of the pre-image is equal to the set. The invariance of a set, which means that the pre-image of a set is equal to itself. And the invariance of a function, which means that when you compose with F, this is equal to the function. Okay? All of them are related to not change when you apply the function in some way. Okay, so if you have an invariant function, you always can create invariant sets. Just take the pre-image of intervals. But why is it? Well, this is invariant. To be invariant, I have to prove that the pre-image of A is equal to A. But the pre-image of this set is the pre-image of the pre-image by F of this A is the pre-image of the pre-image by psi. Well, but this, you recall, you do pre-image, you can write like this, psi composed to F, the pre-image of it applied to I. Well, but psi composed to F, it's precisely psi, because psi is invariant. So you have psi minus 1 by the invariance of psi of I. This is actually A. So the pre-image of A is actually A. So for every interval, the pre-image of it is actually an invariant set. Well, but every invariant set has measured either 1 or 0. The measure of every invariant set, it's either 1 or 0, because I'm supposing ergodicity. The measure is ergodic by hypothesis. So if the hypothesis that the measure is ergodic. So if it's ergodic, the measure of each invariant set is either 0 or 1. Well, either 0 or 1, fine. This implies that the psi is constant almost everywhere. And now I would need, I think to prove it precisely, I would need at least a page or 2. But I'll just give an idea, okay? The idea to prove that this implies that this is the psi is constant is the following. Oops. Try to give an idea in a line. So this is the following. You said that every pre-image of each interval has measured either 1 or 0. So you can write this set X on M such that the psi X is smaller than a number C. This is the pre-image of an interval. It's the pre-image of the interval minus infinity to C. These sets, for each C, these sets are invariant. If you put bigger or equal to C, it's also invariant. Well, it means that these sets are either gonna measure 0, the measure of these sets is gonna be 0 or 1. It's not gonna be all the time 0. Some will be 1. Then you do the following. You take C tilde to be the supremo over all the C's such that this set, let's call this set BC. The set BC, the measure of the set BC is equal to 1. So what happened is the following. There are the measure of the set 0, 1. So there were many C's that were 0, and then there will be many C's that will be 1. But it has to change at some point. Then you take the biggest C when it changed for 1. And this is precisely our C tilde. And this is what we prove. We can prove it's not, after you prove this, is not hard to prove that the C tilde is the C is actually equals to this. This is the constant that PC is equal almost everywhere, because there is the complement that has 0 measure. So it's not everywhere, but almost everywhere. Okay. Well, we use here also that the supreme in R always exists if the sets are bounded. So you have to prove that these sets is bounded. So there is, again, I told you, there is 2 or 3 pages of work here. Analysis is pure real analysis, but the idea is this. So this is always constant. Then it's just missing the last implication. So this is just missing the last implication to show that if psi is invariant almost everywhere, it implies that it's a constant. That's the hypothesis. This should imply that the frequency of visits of a point is equal to the measure of this set. Okay, so fix A, choose some E, choose some E, a set, and define psi as the frequency of visits from X to E. Well, this is actually invariant because the frequency is invariant. We prove that the frequency of E of Fx is equal to the frequency of E to X. So psi is invariant, it's the same image in X or Fx. So this is invariant, but the hypothesis that every time, then psi is invariant. But we prove the hypothesis that every invariant function is actually constant. Then it's constant. So it means that the frequency of E to X, it's a number. It's constant, fine, for each X. But we know the following by Birkhoff's theorem, and here is when we use Birkhoff's theorem. We know the following. Well, we don't know that the frequency is precisely the measure, but we know that the integral of it is the measure. But if the function is constant, the integral of this, it's C. This function is C. So C goes out of the integral, and you are compute the integral over this measure. So it's the measure of the whole space M. So it's C times the measure of the whole space M. But the whole space of M, it has measure 1. That's the measure of the whole space always. So the measure of E is actually C. So C is the tau EX. Okay? So the frequency of visit is actually the measure of the set. So just going back to the statement, now we have completely characterized with respect to sets and with respect to functions. So ergodicity for one side, well, is the measure of invariant. It's always 0 or 1. It's always 0 or 1. By 2, it's actually to say that the frequency of visits is exactly the measure of the set. So we can say it's precisely the measure of the set, the frequency. And we can also say that if every invariant function is constant. So we cannot have an invariant function that's not constant. Okay, so then we can state finally the Birkhoff's ergodic theorem in the ergodic version. That's what should be called the ergodic Birkhoff ergodic theorem, because it's fun that the Birkhoff ergodic theorem, the general version, does not appear the word ergodicity. You don't have the hypothesis ergodicity. But as I told you, the history is because this is what they were expecting. All right. So if you now have
sorry for interrupting. Can you go back to the last slides, please?
Yes.
I think I kind of got lost, but I didn't understand how you related the tau with the psi?
Or with psi?
Yeah.
I define psi, oops, I shouldn't, okay. I did the following. What I want to prove is the following, that if this, I think that's what this is the hypothesis, and this is what I want to prove. Okay, thesis. Okay, if for every invariant measure, every invariant function, implies that every invariant function is always constant almost everywhere, then I want to prove that this equality holds. Fine. What I did? Well, fix an e. This has to hold for every e. Fix an e. Take an e. Fine. Define the psi for it x. Define psi as the frequency of a visit of x to e. So e is fixed. Fine. And then psi actually depends on e. When you change e, you have another psi, but you are defining a function. What we want is the following. If you prove that this function is invariant, then by the hypothesis, it has to be constant. But this is invariant by the way that you defined, because this is actually tau of e fx, which means that this is equal to, you define by psi of fx. It implies that psi is equal to psi composed with f, which means invariance. And then by hypothesis, this has to be constant. So psi has to be equal to a constant almost everywhere. Then, well, if psi is equal to a constant, you define psi with the frequency. So the frequency is a constant. Okay? You use the hypothesis. You just define the psi as the frequency. All right. All right, so this is the ergodic version, and this says what Boltzmann were expecting, that the time average, which is this, it's equal to the space average for each observable which is integrable. An observable is just a function. I mean, map, you act from one space to the same space, and a function you act on R. The image is on R. So the time average and the space average, they are equal almost everywhere. This is actually, now that if you have the result of the general version of Bowen, it's very easy to prove. Actually, the idea is similar to what I just did. I'll give you some idea, at least to give one proof of Birkhoff. No, that is a bit of a cheating, because Birkhoff's theorem is quite hard to prove, but I'll prove this ergodic version. Well, using the Birkhoff's theorem. So by Birkhoff, we have that almost every point, x in M, we know that the limit exists, the limit, this limit is the time average, no? The limit of the time average, theta. So on, phi fjx, I'll call it exists, so I'll give a name for it. I'll call it f tilde x. For it x, I call it this as asymptotic average, the f tilde x. This always exists. And moreover, Birkhoff also says that this average, well, it's invariant. It's not hard to prove because it's just a change here on the J, on variables, a change of variables. So this implies that phi tilde is invariant. Okay, so almost every point we define this function, which is the asymptotic average in time, and this is invariant. Well, just put here x in the place of s replaced by fx, and then you can rearrange and this take the limit. It's the same computation that we did before. Fine, this is invariant. But if mu is ergodic now, mu is not invariant only, it's also ergodic, it's stronger. We just proved that, well, mu is ergodic. Every time you have an invariant function, it has to be constant almost everywhere by the proposition that we just proved. It's equivalent of the ergodicity. So if this function is invariant, then it's constant almost everywhere. So for almost every point, this is constant. Well, but Birkhoff's theorem also say that this, when you integrate this average with respect to mu, this is precisely the integral of the map. Well, yes, not of the map, of the function, sorry. This is precisely the integral of your observable. Well, but this now is constant. This is constant. But if it's constant, this is C. Well, but this is, if it's constant, you can take it from out of the integral, and the integral of the whole space is 1. So this is equal to f tilde x. So this proves that actually the time average is precisely the integral. You don't need to integrate because each point has the same, everything is constant. So since the time average is constant, you have the result of Birkhoff. This is just because ergodicity, what we use here is that ergodicity is equivalent to every invariant function has to be constant. There is no other way. When you have ergodicity, every invariant function has to be constant almost everywhere. This is quite strong because you are thinking of including a probability measure that has some property, and this property forces to every function that you define on your space. If it's invariant with your map, it means that when you compose with your map, it doesn't change, it's equal to the function. So this has to be constant. There is no invariant functions that are not constant. So it has to be constant. It's strong. So this ergodicity brings is really strong properties for your dynamical system, and from different point of views. You could think of functions. You could think of sets. So there are many ways that you can approach the definition of ergodicity and bring some other results. So let's try to revisit some of our examples that we saw already and try to see some nice applications.
Okay, I have just one question here. I'm not
please.
sure my question makes sense or not. If we look at the expression of Birkhoff-Ergodic theorem, the left side, we can see its kind of point is appear, x is appear in the left side.
Mm-hmm. Mm-hmm.
But if we look at the right side, it's just the integral with respect to the measure. So it's kind of maybe some kind of confusion. So I'm not sure I'm asking a valid question or not, but can you say something about this?
Well, this is the Birkhoff-Ergodic theorem pointwise. Let's say like this. Well, that's precisely what is the difficulty of Boltzmann, because when you in the right side you are saying that there is the integral of the whole function, so you are integrate over the whole space.
Yes.
And they are in the left side, so you are considering all the points, more or less all the points. You are taking all the points.
Yes, almost every point. Yes.
In one side, you are considered just one point. You fix one point. For every point, you have the same thing. For almost every point, you have. What he says is the behavior of a point under some observable. It's similar to every point because actually it's equal to the integral. When you have ergodicity, you have some kind of strong the distribution. You can think in a very rough way. The distribution of the points are similar. You have some similarity of the points. Almost every point behave more or less in the same way, because you have that when you take the time average of a point, you're right. It depends on the point. It should, but it doesn't actually, because it's equal, when it's ergodic, it's equal to the integral. So every point has the same probability of happen something. So for instance, if you choose a point in a set, the measure is ergodic. If you choose a point, so almost every point has the same frequency of visits to a set. There is no difference of the points. The measure, if you are in some positive measure, the measure does not distinguish between the points. That's I think what you are asking. I don't know if I managed to answer.
Okay, thank you.
Yeah, I guess that's actually the care of the Boltzmann hypothesis. What he wanted is this, that there is no distinguish between points. All right, so let's recall the continued fraction expansion. And remember, you get a point in 0, 1. You can extend to the whole line, but let's start by 0, 1. And you want to approximate by rationals. So the best approximation that you have, it's given by the continued fraction expansion. Well, there is a process. We write this, and what we mean by it is to say that x0 is the limit of the sequence, let's say xn, where you erase this part. So it's x0 is the limit of it. That's what I meant. We explained this last class. We can model this algorithm using a map. So we have the Gauss map, which is simply you take the fractional part of 1 over x. And then if it's 0, you just define as 0, the image of the Gauss map. So you have this graph. So in the intervals that you divided the intervals, and then you have this map. Well, to model then the algorithm, what you do is the following. Well, you define by recursively that xn is actually the nth iterate of x0. And to define the an on the expansion, we call that there is this an, that are the numbers that approximate the numbers that appear in the expansion. To define this, you just say that the gn minus 1 has to be in the ian. We call that ian is the interval that are of the form 1 over an minus 1, 1 over an. It's not an minus 1, it's an minus plus 1. Plus 1, I said minus, it's plus, an plus 1. All right. So recall also that we defined the measure on this space 0, 1, that actually it's invariant under the Gauss map. Well, actually it's ergodic. This measure, when you consider, I defined it first with a C here, but I said that if you consider C equals to 1 over log 2, this is a probability. So this is it's a probability that is ergodic. And we proved that using Poincare recurrence theorem, we proved that, for instance, choose a number, 7. So 7 appear infinitely many times in the expansion of continued fractions. So this is not hard to prove using Poincare theorem, because you consider this, well, if the 7 is in the continuous fraction expansion, it means that you could think that, okay, your point start, you have your number 0, let's say, and then your point, the an has to belong to this interval 1 over 8, 1 over 7. Okay. But the measure of this interval with this measure is actually positive. The measure is actually positive. Well, if the measure is positive, Poincare theorem says that every point returns to this set infinitely many times. But if Gn belongs to this set infinitely many times, it means that An, because to belongs to the set, it means that An is 7. So it means that An is 7. It means that 7 will appear infinitely many times. So by Ponca theorem, we can say that, well, infinitely many times in almost every number, 7 will appear in the continuous fraction expansion. But now we can have a better result. Now we can say precisely which frequency the visits are going to happen. Because 7 can appear infinitely many times, but appear 1 7 now, and then in 10 million digits, and then another 7, and then 100 of 7s, and then another 7 after 10 millions. So what's the frequency? Well, the frequency it's 1 over log 2 log 6463. Well, this is very easy. It's a very easy exercise that I want to do, because when we have easy exercise, it's good to be done. We just proved that the frequency of visits it's defined by, just prove that let me rephrase. It's too easy, and then I got confused. So we want to prove that the frequency is this nice number. Fine. To prove the frequency of 7s to appear is this nice number, we know that we have to check the interval, that is 1 over 7, 1 over 8. So what we want to do is the frequency of the visits of a point to this interval, because every time that a point is going to get a 7, every time that visit is I, let's call I7. No, because we defined An as the Gn of x0, xn equals to Gn of x0. So if to get a 7, you have to visit this interval. So we want to actually compute the frequency of visits to this interval. That's what is going to give out the frequency of 7s. Well, the frequency of visit is actually the measure of the set. Well, but the measure of the set is very easy, because it's 1 over log 2 of the integral of 1 over 8, 1 over 7. You integrated the interval, the map 1 over 1 of x dx. And that, even my students of calculus 1, I hope at least, they can do it. So let's compute it. This is the log, the integral log of 1 plus x. And you apply it 1 over 8 to 1 over 7. So this gives you 1 log 2 log 1 plus 1 over 7, it gives you 8 over 7 minus log of 1 plus 1 over 8 gives you 9 over 8. Well, but you have this nice property of logarithms, that you have this minus this is the quotient. Then you have the quotient of 8 over 7 divided by 9 over 8. So you have 8 times 8 and 7 times 9, and then gives you precisely 1 log 2 times log 8 times 8, it's 64, and 7 times 9, it's 63. If I didn't do any wrong computation, so that's it. So then we can precisely compute. And if you do any other digit, choose another digit now, well, you see that you get the same thing, no? So you can just repeat the computation and compute the frequency for each interval. Okay, so this is a quite nice and simple example that after Birkhoffs have done all the work, we can prove it. Think about how we'll do the proof. Maybe you can do it over the weekend and try to think about how we'll do the proof that the frequency of 7s to appear in the continued fraction expansion is actually this number without Birkhoffs theorem. I imagine that if you're not so expert in number theory, you probably appreciate Birkhoff during the weekend if you try to do this exercise. Okay, so I'm almost done. I'm afraid that I'm taking over my time, but just to finish some examples, it's quite quick now. So recall the decimal expansion. So the decimal expansion map is simply the fractional part of the 10 times x. So this is ergodic under Lebesgue. We saw that Lebesgue is ergodic for it. And then I told you last class that, well, there are numbers that are balanced and there are numbers that are not balanced. A number is balanced if every digit appears with the same frequency of 1/10. Well, most of the numbers actually are balanced. So the universe is balanced. Most of the numbers are balanced because the Lebesgue measure of the set of numbers that are not balanced is 0. Well, I was going to prove it, but I don't have time. So then I leave this as an exercise for you. It's nice exercise. You just have to I'll give you one idea. It's just to think that you have to, the set that you have to measure, you have to consider the frequency to a set, no? The frequency to a set. And these frequencies, you have ergodicity, this frequency is the measure. And now it's Lebesgue measure, which is the length of the interval, if it's an interval. So the set that you want to measure, it's actually the interval j/10, j+1/10. So the probability of appear at j is the measure of this interval j/10, j+1/10. Then you do it between 0 and 9, j varying between 0 and 9. You get a full measure set for each j, and then you intersect these, is going to be a full measure set for the whole space. So with Birkhoff's theorem, this is a simple proposition. But again, this is nice because most of the points are actually balanced. Most of the numbers have a balance. We know that, I imagine that pi, it's not proven, but I imagine that pi is not balanced. This is just a guess. There is no proof to it. But I think that should not be balanced, but most of the points are balanced. I don't know, you can guess different. If you have another guess, you can tell me. Okay, just to finish, this is the last example. Recall the circle rotations and recall that you have a circle, you just rotate it clockwise with the angle alpha. And Lebesgue measure is invariant for it. Lebesgue measure on the circle is just the length of the arc divided by 2 pi. So there are very much difference for rotations, big difference if alpha is rational or if alpha is irrational. If it's rational, all the points are periodic. If it's irrational, all the orbits are dense. So the dynamic is completely different. And this, it must be seen by the measure. It cannot be unseen by the measure. Otherwise, our ergodic theory was not good enough. And this is, it's seen because the rotations, they are not ergodic with respect to Lebesgue. If alpha is rational, but if alpha is irrational, then it's ergodic. So the dynamics, it's mirrored to the measure. So when the rotation is very simple, you don't have ergodicity because ergodicity is a stronger condition. But when the dynamics are quite complicated in the pink case, so then you have ergodicity. Well, and then if you have ergodicity, you for a irrational rotation, you can prove that you choose an interval, and then the frequency of visit to this interval is this limit, and then you can compute this as the measure, Lebesgue measure of the interval, but the Lebesgue measure of an interval is simply the length of the interval. So it says that each point visits this interval with the precisely frequency of the length of the interval. And that's just for, I think I already mentioned, it's just to make a parallel between Ponca theorem and Birkhoff's. So Poincare theorem, we can call a qualitative theorem. And Birkhoff's we can call a quantitative theorem. Poincare tells you, take a set inside of a big set, big in which sense, the measure is positive. So you know that a point is gonna visit this set infinitely many times. A typical point, a point that is in a set of full measure, a typical point is gonna visit infinitely many times. But Birkhoff says more. What Birkhoff says, well, it's gonna visit infinitely many times, but with the frequency, well, it's gonna spend some time outside and then it's gonna enter. And then it's gonna spend the same time outside and then it's gonna enter. So it tells you precisely the frequency. And this frequency, when you have ergodicity, is the same as the importance that this set that you fix have. Is in the case of Lebesgue, is the length of the interval. But in general, is the measure of the set. So this gives you a more quantitative, a more precise result, facing the versus the Poincare, which is more qualitative. But qualitative or quantitative, they are both good. It depends on what you want, what's your problem. So depending on your problem, you really need quantitative, but maybe you don't need, you need more qualitative results. So of course, ergot theory goes beyond what I have showed for you. But these I expect to give you the first impressions and the first ideas, and well, thank you for your patience and thank you for continue coming after all the lectures. And I hope that we could well understand a bit at least of the beginning and could appreciate. And I hope that many of you, or at least a few of you, play a bit in this world of ergodicity. So thank you.
Thank you very much, Jaqueline, for this wonderful mini course and last lecture. So let's thank Jaqueline with a applause.
Thank you.
So I'm sure the student also can, if you have some more question in the future, you can contact Jaqueline. So if today, time difference is late in Europe, you have some question they are not completely formulated, you can still write to her in the future, and we are here next month, so you're welcome. So there are any questions today for Jaqueline? Don't be shy, some of you already have some question.
There's no question from me, but can you share these notes or slide with us? Maybe we can take a look. And we have received the first lecture.
Yeah, I will send you the second one that I have to send you, and then Jaqueline will give you the third and the fourth lecture. No? I will send you all together, and I will post.
I think the third one I gave you already.
No, I didn't. Yeah, okay. And I will post in the website. Okay, so I will send you, but I will post in the website.
Okay, thank you.
I'll try to. The proofs that I wrote on, because I sent to Stefanella on the PDF. But if I have a bit of time over the weekend, I'll try to write on a bit nicer on the proofs that I made and then put together with the slides. Yeah. So this is to make people a bit less shy to ask questions. I'm sharing with you a picture of Rio. That picture I took from I forgot how to say bondinho. It's a